Well, thanks for inviting me. I will talk about domain-specific languages of mathematics. And that's both a research project and a course, and since a year back also a book. So first, a little bit about myself. So I'm a computer scientist, a professor at Chalmers University of Technology. I'm a Haskell hacker. Haskell is a functional programming language that you will see a bit of in this mini course. I like to connect the big picture with formal details. In language technology, I worked on proving, so formal proofs in another language called Agda, but also on the applied side on climate impact research together with the Potsdam Institute for Climate Impact Research. I worked on parametricity, testing, parsing, programming, and then most relevant for this talk, domain-specific languages of mathematics. So now what is that? Well, first, as I mentioned, there is a book. It's the front page is on the left. I'm the main author and I got 2 co-authors. It's also the course literature for a 7.5 credit course at Chalmers and University of Gothenburg. And the main idea is to encourage the students to approach mathematical domains from a functional programming perspective. And we'll see more of what that actually means later. And students will learn about the language Haskell, identifying main functions and types involved in different mathematical concepts, introduce calculational proofs, pay attention to syntax, semantics, and organizing the results in what is called the domain-specific languages. And the mini course today and tomorrow gives a bit of a teaser, some functional programming in Haskell, and a few examples of lectures from the course. And clearly, 8-week course cannot be crammed into 3 one-hour lectures. So if things are difficult, then just ask and I will just slow it down and make sure that we get through at least some parts with a good understanding. So clearly, the concept of a domain-specific language, abbreviated DSL, is central here. And one usually says that a DSL has 4 components. A surface syntax, so the sort of the words and the grammar of the language, and that's mostly ignored in this course. But formally, it's a set of strings defined by some grammar, things you can write. The next level down is the so-called abstract syntax. That's usually implemented as a recursive data type of syntax tree. And then there is a semantic type, the thing that the language is supposed to describe. And you can model that as a type or a set of values for the syntax. So semantics means meaning. And then the actual semantics is a function, a normal mathematical function, usually called eval for evaluation, that takes the abstract syntax to the semantics. And to make it slightly more concrete, here are 3 examples. The first is date expressions. So 2023, 08, 30, or the last Wednesday in August, or today, are all strings, so surface syntax for, well, today. And you could, in many computer applications, you need to handle dates and expressions involving dates. And that means that you need to be able to implement these. You need to define formally what they mean, what the semantics is. And it's worth noting that it's clear from, for example, today or the last Wednesday in August, that they cannot be defined without some context. So today is not a fixed date. It's always, it can be implemented as a function from a current date to some the date you mean. So the last Wednesday in August, for example, will be different times depending on which year you're in. Okay, next example, language or category, domain that you can code up is Excel sheet formulas. So if you haven't worked with Excel, here are some examples. The sum of the cells A1 through A9 or the right part of the left part of cell C7 if you want to do some string calculations and so on. That's also a specific domain, and the semantics there is perhaps a function from an array of cells into the value of the cells. Then first order logic. Then you have expressions like P implies Q, or for all epsilon, there exists a delta such that, for example, here, epsilon is bigger than delta, which is true, but not very interesting, perhaps. And those kinds of expressions also form a language, a domain-specific language for logic. And then you can have the semantics as truth values. Okay. And the mini-course overview, this is just an intro here, is then a short introduction to what one might call type-driven development. You might have heard about test-driven development. So you start with writing some test cases. You want to implement something, and then you start filling in code, and you continuously check if the code actually satisfies those tests. And here I'm trying to start with writing a type, which is something that a compiler can automatically check if the program satisfies. And that takes us to the domain of typed functional programming, where the language Haskell I will use is a prime example. It's a very nice language. It's been around for 30 years, but it's a very modern language nevertheless. I will talk about function types, polymorphism, and function composition, pair types, and this type-driven development, and also what's called sum types, which are not as common as the product type of pair types. And then I will also give some another kind of examples where in the course we often come back to some course book, some mathematics book, and take a quote and try to analyze it very carefully. Like the devil reads the Bible, you sometimes says. And it's like trying to see exactly what's written and what does it mean and can we code it up. And the first example there is on complex numbers. And there we okay, now it's in progress again. That's good. Okay, so hopefully you can now see an editor window. On the left-hand side is some text, and on the right-hand side is mostly empty. It's basically a strong calculator, and that's the interpreter for the language Haskell. Well, you see, I've written 1 + 2 there and returned 3. And I should ask at this point, can you see, or is the font size far too small? So if somebody would be daring enough to write something in the chat or say that it's okay or that I should increase. Okay, somebody says it's okay, then I'll hope that you complain if you think otherwise. So first of all, I'm using something called literate programming. Literate programming, oops, which has been around since the 70s or so. It means that anything I write outside code blocks is a comment. So this part is a comment, and then it says begin code, and then there is some code and end code, and then it's comment again. So I can say comment again down here. So that's just to make sure that there is plenty of space for explaining the code and not only typing code. And this first code block is something I will actually not really explain. I would just say that it's part of the kind of first few lines of a file that you would have to add if you have certain requirements on what you want to import and what you want to use and so on. So I will now hide that part and focus on starting slowly with some test functions. So this part here is going to introduce some of the concept of the functional programming language Haskell. And functional, as I should say, functional programming language. Functional means it's based on functions. And based on functions means that we really have to experiment with what functions can do. So F1 here is a function, and it's colon says means, I can say here, means has type. So this F1 has type int arrow bool, meaning it takes an integer as an input and returns a boolean as the output. Whoops, now I'm accidentally moved to the end of the whole file. I'm back here, F1. Okay, now I'm on the right-hand side and seeing, okay, F1 applied to 7. And that says false. Why? Well, because I defined F1 to be the predicate even. It's a built-in function in the Haskell prelude. It checks if an integer is even or odd. I wrote here F1 parentheses 7 end parentheses because that's the usual way functions are written in math books. But function application is so common in Haskell that you don't actually have to write the parentheses. So F1 of 7 works just as well. And if we want to try F1 on 6, then it says true, not very surprisingly. 0 is also true, and so on. Okay, another function, and I should also mention I have indented, I added spaces here just to show that there is something matching between F1 and F2. So F2 is a function that produces an integer. So this is a consumes an int, and this function produces an int. And if I want to use F2 on 3.14, for example, I will get 3. It just rounds it. And that's the definition here. It says F2 equals round. I should also note that I can write F2 equals round. I don't have to say F2 of x equals round of x. I can work on the level of functions. I can give names to functions. I can pass them around and work with them. So that's one of the features of functional programming. So it's rounding. So if I say instead 3.85, I will get 4. Okay, and then as a last example of this very basic intro, let's see, can we combine F1 and F2? So get from a double all the way to a Boolean. It may be not very useful function, but the intention is to first round the number and then check if the result was even. So here it says error to do. So this is a complete definition, but not a very useful definition. If I say F3 of 3.14, it will say exception to do blah, blah, blah. So clearly I need to replace this with some implementation. And the comment here says I should combine F1 with F2. So now there are different ways of doing this. And the simplest way is saying, okay, F3 takes an argument, which is a double. Let's call that number x. And F3 applied to x should then be, well, according to the type, a Boolean, so true or false. The way we can construct a Boolean is by using 1. So let's say, okay, this is F1 of, and then some question mark. Well, what question mark? Well, we have to use F2 to get an integer. So let's use F2, and that we apply to x. So here I've used parentheses. I said before I don't need them when function application, but I do need them when it becomes ambiguous. If I wouldn't use parentheses here, it wouldn't be clear what F1 was applied to. So F1, the function, should be applied to the result of applying F2 to x. Okay, let's try this one. So F3 on 3.14 is false. So why is it false? Well, first it rounds it. It uses the rounding function, and then it checks if the result is even. And the rounded 3.14 is 3, which is odd, so it's not even. Okay. I should also mention one more thing, and that is anonymous function expression. As functions are so important, it's actually possible to write functions without naming them immediately. So this is also called the lambda expression. And the syntax is you have a backslash and then a variable like x and then an arrow and then an expression. And in this case, for example, f3 here, you can say, well, f3 is equal to the lambda expression that takes an x and returns f1 of f2 of x. So this is the same function as before. I can still call it on 3.14 or 3.85 or whatever. But I can now calculate with functions a little bit easier. So if f3 is used somewhere, I can replace the use of f3 with this function. I should also mention that Haskell is not just a functional programming language, it's a pure functional programming language. And pure here means no side effects. So what is an example of a side effect? Well, printing or parsing or random number generation and so on are side effects. And you might then think that, oh, we can't do any of those, but you can. It's just requires a bit of care and some other types that I will not go through today. But an example of something which is not a function in Haskell is if we say random. And we say that random would be something that takes a natural number and gives another natural number, with the idea that random 6 would give a number between 0 and 5, a random number. So that's a function that's available. Maybe you would usually write it like this in some other language. It's often available, but the problem is that this is not really a function in the mathematical sense, because if I call random 6 2 different times, I can get different results, but the function cannot ever give different results for the same input. So random of 6 could be equal to 2, and then the next call of random of 6 could be equal to 5. But 2 is not equal to 5. So there's sort of error. There's something bad happening there. So random there would be a side effecting function. And that's something that is not allowed in this type system. Okay, any questions so far? Okay, good. Okay, squaring. That's a simple function that might be useful just to implement something ourselves. So x to the power of 2. Square of 3 is 9. Square of 17 is 289, and so on. So this shows that if we want to implement simple mathematical functions, it's well, it's almost directly math syntax. We might have a function g of x, which is 1 plus x, 1 plus 2 times x plus x squared, for example. And then g of 3 would be 1 plus 2 times 3, which is 7, plus 9, which is then 16. Okay, and if you want to exemplify these lambda expressions again, this could be written lambda x arrow, and this could be written lambda x arrow. And notice I say lambda is approximated. I should say probably ASCII approximated by the backslash, and not the Greek lowercase lambda. Okay, that was the simple examples of functions. Now to some type-driven development. So here I want to use what is called parametrically polymorphic types to guide the implementation. And I should say that the functions I define here are sort of trivial functions. But they are still useful, and especially they are useful for illustrating the point. So the first function I'm going to define is called id. Id for identity. So the identity function takes an argument and returns the same value. So it sort of doesn't do anything. And it's defined here as just error, which we clearly have to replace. But it is a function. And any function, then we have to say it takes an argument x, or we could define this as a lambda expression. And then we have to return something. And now we can start thinking, what type is the result? So the type signature here says A to A. And that really means for all types A, take an input of that type and return. I should continue here, I guess. An answer of that same type. So we don't know, though, when we implement this, what type A is. And that has very strong implications. We cannot return 3, for example, here. If we would try, Haskell would complain and say, well, there's something fishy going on. We can't return a string similarly. We really have only one choice of a correct value to return here, and that's x. So we have x of type A, and if I sort of indent a bit, you can see, so x is of type A, and we return x of type A. So that's the only type correct and complete definition of the identity function that we can produce. And now, of course, if you want to run this definition, it's not very interesting. We say identity of 3, that's 3. Identity of 7 is 7. But one thing is interesting, and that's that we can apply it to other kinds of things as well. The identity of hello is hello. The identity of identity, well, it's the same function, identity again. So I guess identity of hello is hello. We can apply identity to anything, a pair of a number and a Boolean value or whatever. So the type polymorphism here, polymorphic is between many forms, means that it's the input to the identity function can have many different forms, and whatever it has, it will return the same result. Okay, now to const, the function const, and already given the type here, we have to understand what A and B mean. So A and B are 2 arbitrary types. So we don't know what A is and what B is, and the function definition must work whatever A and B we put in. But it is a function from the value A, and it returns a function from a value of type B. So we can start saying, okay, let's assume we got an x. That's a good starting point. X is of type A, and then we have to return a function. So let's write a function here, lambda y arrow. Then it's a question, what can we put in here? So at this position here, we need a value of type A. So the first thing we can try, which will not work, but just to illustrate it, is to return y. And then it will say, well, we give a long error message saying, basically, you couldn't match type A with actual type B. So you tried to return a value of type B, but you needed something of type A. So the only thing we have of type A is x. Okay, now it does work. So we defined a function here, const, which takes a value and then returns another function. So it's if we try to use it, we can say const 2. Well, const 2 is still a function, so we have to apply this function to another argument. Const 2 applied to hello, for example, and that will return 2. And actually, it will throw away whatever we write here. So we can even say error don't touch, and it will still return 2. And this is an illustration of what is called laziness. Laziness. So Haskell is a lazy programming language, meaning it doesn't evaluate things until they are needed. So here is an example. The error message here would be printed, don't touch would be printed if it actually needed its second argument to const. But the function const takes x, it takes y, and returns x. It never even touches y. And that means we can get around using it without evaluating the second argument. Okay, so these functions are sort of boring functions, id and const, and this dot, which stands for function composition, is actually a really useful tool. And it has a little bit more complicated type. So first we can dig into the type a little bit by erasing some parts. So there is something to something to something. So it has 2 arguments, this one and this, and then returns something else. But the 2 arguments it gets in are actually functions. So it's a higher order function. Dot is a higher order function. A function taking functions as arguments. That's usually called an operator in maths. But it's in Haskell is just an ordinary function with a special type. And the other thing is that I've written parentheses around the dot here, and that's because if I use operator characters like plus and dot and minus and so on, I can use the function infix. So the function is called dot, and it can be used between its 2 arguments. So if I say f dot g, now that is calling the function dot with 2 arguments, one called f and the other called g. So here is then the stage where we're going to have to fill in a function from A to C. And it's interesting that I said informally this should be function composition. You should compose 2 functions together. But I haven't really said what that means. But given the type, this polymorphic type, there is actually no choice but to do the right thing. So let's explore that further. So first, what is the type of the result? So the result here, maybe we can call it foo, and then we can say where foo equals something. So foo has type A arrow C. And that means that, well, foo is a function. It takes some x input and it returns some value of type C output. And we know that x is of type A. But we have to produce a value of type C, and the only producer of C's is this function, the first argument to the composition, so f. Because we know that f has type B to C. Maybe I should indent this. So we can try to use f here on what? Well, to get an input here, maybe call it that bar. So we have to find some value bar, which is of type C. No, sorry, of type B. So why B? Well, because the input to f is of type B. Well, how can we define something of type B? Well, then we have to use the other function, the function g. So let's add that comment as well. So the function g takes an A and returns a B. So this bar is g applied to something of type A. Now, what do I have? Well, I actually have an x. I can apply g to x. Now let's try to see. Variable not in scope. Yeah, okay. I have to make this a local definition for foo. So foo where bar is equal to g of x. Okay, now it's happy. So this is a little bit indirect, but what I was trying to say is that we have to create a function. That function takes an x and it applies f to a result which it gets from g. And now I can start using program calculation here. So we know that bar is equal to g of x. So I can just replace bar by g of x. Okay, and now we can use the anonymous functions, the lambda expressions, to say that, well, actually foo is equal to lambda x arrow f of g of x. That still type checks and works. And then if this should be foo and foo is this, we can just replace foo as well to make it a bit shorter. So what do we have here? We say that f composed with g, so f after g is the usual reading, is the function which takes an x as an input, sends it into g, and lets the result go into f. Okay, and here it says redo f3 using dot. So let's split the screen a bit and search for f3. So we defined this function before. So I'll now move it down here and call it f3 prime. So if we look at the pattern here, we can see that, even if I even indent it similarly, we can see this is lambda x arrow f1 of f2 of x. So that should be possible to write with the new combinator, with the new dot here. So if we just rename f to f1 and g to f2, then we get exactly this. So we can say f1 dot f2. So now let's see if we can test the function. So we have f3 prime on 3.14, and we have f3 on 3.14. And not surprising, they do the same thing. So what have we done here? Well, we've implemented 3 polymorphic functions, and especially the last one is really useful in programming. You very often want to thread values through 1, 2, 3, 4 functions. Sometimes in shell scripts and so on, you use a bar, a pipe sign, a vertical bar for this, but here it's a dot. And it really shows that you can work with functions as first-class values. So dot takes 2 functions as input and returns a 3rd function as an output. And we also mentioned in the on the way there that it uses, we also have laziness around, and that dot is a higher order function. Okay, let's see time-wise. Yes, we can fit one more part. So this was part 1, just polymorphic functions, and let's then move on to pairs. So a very common concept in mathematics is Cartesian product. So here's the mathematical syntax. If you have 2 sets, A and B, you can form the set A cross B. And that is all the ordered pairs of values x and y, where x comes from A and y comes from B. So the typical example, I mean, if we have the set 1, 2, and then I don't quite know how to create that Unicode symbol, cross it with, say, A, B, and C, then we will get the pairs 1A, 2A, and 1B. Maybe if I line them up, it's easy to see the pattern. 1B, 2B, 1C, and 2C. So 2 times 3 values becomes 6 values. So that's why it's called product. So the product of sets, the cardinality of the product is the product of the cardinalities. The number of elements is multiplied. So the Haskell syntax doesn't use this infix cross, which is one of the Unicode characters that I don't quite know how to write, but I can copy it at least. So the Haskell syntax instead uses the same parentheses as for the pairs. So the pair type A, B has values as pairs X, Y, if X has type A and Y has type B. So if I try to write here 1, hello, that's just a pair of an integer and a string. And well, I can ask for the type of this just to show that. Oh yeah, it's a little bit more general than that. It doesn't have to be an integer. It could be some other kind of numeric type. But if I claim it's an integer, it will say it's an int and a string. Okay, so then let's try to do some type-driven development again and implement the function first, which is abbreviation for first, so the first component. And so first type says that if we have a pair of an A and a B, we should return an A. And already here, the name might give a hint, but the type forces the implementation. We have only one choice of a correct implementation here. And nicely, we have what is called pattern matching. As we know that the input function first is a pair, we can write, okay, it takes X and Y as an input. And then it's question, what can we write here as the output? Well, the only value which is correct to write here is X, because X has type A, while Y has type B, and those are the only polymorphic values we have in scope. So if we try this, it's sort of worked, and then we could say, what is first of this pair? Well, not surprisingly, it's the 1. It extracts the first component, throws away the second one. And given that, it's not very surprising to see that we can also implement the other component. If we accidentally would write X here and try to load it, it will say, well, couldn't match expected type B with actual type A. And then it gives lots of suggestion for what to do about it. So this really has to be Y. Okay, and now that works. So now we can also do, we had first, we can also do second on this pair to get the hello out. Okay, so a little more complicated. We're building up towards more complicated functions. The swap function has this type. It takes a pair of A and B and returns a B and a BA pair. So we can pattern match on X and Y. And not surprisingly, the only thing we can do on the right-hand side is to return Y and X in the opposite order. So now if we take the same value and swap, then we got hello 1 instead of 1 hello. And well, we could call swap twice if we want. Then we get back the original pair. Okay, and similarly, if we want to implement something like associativity of Cartesian products, so we have a pair of an A and another pair. We can move the things around to create a pair where the first component is a pair and C is alone instead. And here it's an X, a Y, and a Z, and there is very little choice. We have to produce an X and a Y followed by the Z. Okay, these were warm-ups, and now we get to the more complicated version. So again, a higher order function. So we have to first try to read off the type here. So F to P, it's a, well, it's not a very good name perhaps. It's just something that takes a function and returns a pair. So maybe we should say as a comment, function to pair of functions. Because the input, if we, I wanted to sort of erase some of the information here and say that, well, it takes something and returns two things. So that at least gives us the help that its input here, we can call it f. So if we have one argument to the function f2p, and we could call that f. And notice f is in turn a function of this type. But then we're supposed to return a pair. So we can say, okay, it's a pair of foo and bar, where foo equals something and bar equals something. Now, we can try to see from the type up here what the types of these arguments are. So the first one, whoops, foo has type A to B. And the second one, bar, has type A to C. So we should take a function as input, and we should return two functions, foo and bar, as output. Okay, how do we define a function? Well, we give it an argument, x. Actually, in both cases, we can give it an x. And then in both cases, that x is of type A. So we can have that as a comment here, x is of type A. And then we need to return something of type B in the first case. And now you might wonder, how do we get a hold of a B? The only thing we have is the function f. So if we call f, so we can make one example here, if we call f on x, that will have type b, c. So that will be a pair. But then we can use our helpers here. So we can take first of that pair. So foo of x can be defined as first of f of x. And similarly, this should be the second of f of x. So we have locally defined two functions, foo and bar, and they both call the same helper f, but one takes out the first component and the other takes out the second component. Okay, let's see if we can, well, okay, before we run it as an example, let's first try to make it a little shorter. And the reason I'm working with shortening here is not necessarily that it needs to be very short, because it might also be difficult to read if it's short, but it's definitely easier to calculate with. So I can mention here program calculation. So just as you can do like x times a plus b equals x times a plus x times b, the distributive law. These kinds of calculations can also be done with programs in Haskell. And it's easier to do calculations if the programs are short. Program calculation is easier with short notation, with brief, notation, I could say. So let's see if we can make this one slightly shorter. So first, I can use the anonymous function trick. So this can be a function, lambda x to first, I'll also cut the comment here. And then bar similarly takes an x in and returns second of f of x. So this means I can replace the definition of foo with the right-hand side. And similarly, I can replace bar with this expression. And now it's a one-liner. I can make it a little bit better still, because this pattern we've seen before. So if I split here and return a search back to the composition function. So remember, we did this, we noted that, well, actually, when we have a lambda expression, which applies one function after the other, we can just remove the lambda expression and use the dot infix instead. So in this case, it means that this lambda expression is the same as first composed with f. And this lambda expression is second composed with f. And now we truly have something short. So the whole function f to p takes a function in and returns the composition of first and the composition of second with that function. Okay, so this is trying to show that you can, by just having a polymorphic type, you can sometimes find the implementation and there is almost no choice at all. So the implementation here is forced by the polymorphic type. And still, this is a rather abstract type, so we may need to exemplify it. So I have some examples that we can use below. So let's cut this part and then try to see if we have some example. So I got, for example, okay, this is the other side. Let's implement an example first then. So if I want to use f2p, I have to have a function that takes a value and returns a pair. So let's call myFun. They take, say, an int and returns both a bool and an int. So myFun of some value n is equal to even of n. So it checks if the number is even or not, and n plus 1. Okay, so myFun of 3 says false and 4, and myFun of 4 says true and 5. So this is a function which can be used with f2p. So test1 equals f2p of myFun. So what is now test1? Well, test1 is a pair of two functions, from int to bool and from int to int. So we can say, for example, first, well, let's give them names. So test1 f for first is first of test1, and test1 s for is second of test1. And then I can actually also insert the typings here. So test1 is a function, well, it's a pair of functions, one from int to bool and one from int to int. And these then are of those types. Test1f as type int to bool, and test1s as type int to int. So let's try test1f on 3. It says false. Well, why? Well, because it's actually is really the even check. So it does it a little bit of a roundabout way. It first computes even and n plus 1, and then checks if the result is even, if the first component is even or odd. But you may remember that we said that Haskell is lazy. So when we do this first component computation, we actually will not compute n plus 1. It will only compute and check if the function is, if the value is even. And then test1s of 3 is 4. So that's the function which takes n and adds 1 to it. Okay, I have a few minutes left, so let's do also the opposite function. So if we have a pair of functions from the same set A, we can create one function which computes both at once. So in this case, we got a pair. Actually, we can pattern match and say this is f and g. So we're given two functions f and g here, and then we should return a function from x to a pair of some high and ho, where high equals something and ho equals something. Okay, so what's the type of high? High has type B, and ho has type C, the second component there. So we can maybe even indent this to see that things are sort of lined up nicely. So we have an X of type A, and we want to produce a high of type B and a ho of type C. And the two things we've got in our sort of arsenal, in our toolbox, are F and G. Those are functions from A to B and from A to C. So clearly, if we want to produce a B value, we have to use the first function, F. We can apply it to the X. And in the other case, we can apply the G function to the same X. And as you might see, there is not really any reason to have a separate where clause here. So I will now remove the where clause and insert the definitions directly to make the code a little shorter. And now we have a function P to F that takes a pair of functions F and G and produces one function which does both. And then we should be able to run. So I think we got an example down here of a pair, x1. So x1 is a pair of functions from integer to integer to bool. So we should be able to run P2F on x1. And it says, okay, yeah, sure, that one is a function. But the function needs an integer. So let's apply it to 3, and then we get 4 and false. So notice here that we applied the higher order function to the example of two functions. We get a result, which we apply to 3. So you can read this as P2F x1 applied to 3, but Haskell doesn't require those parentheses to be in place, so it's enough to write directly P2F x1 and 3. Okay, and now the final step here I want to illustrate, which is also related to calculation, is that we can combine these two functions, P to F and F to P. So take a function, create a pair, take the pair and create a function again. So let's see. So I said this in the wrong way. P to F. Yeah, so take P to F creates from a pair a function, and then it creates a pair again. So what here, which is like, okay, what on earth is this doing? What should be applied to a pair? So for example, this x1. And then it gives back something of the same type. So if we check what the type of x1 is, it has the same type. And in fact, it is the same pair. So how do we see that? Well, we could do a little calculation, but we could also just test it. So what of x1 is a pair? So we can take the first component of this pair. That's a function. Then we can apply it to 3, and we get 4. Or we can apply the second component to 3, and we get false. And false because it's not even. We had here the definition of the pair as the +1 function and the is even function. So basically, x1 and x2 is the same pair, but they are a pair of functions that are not all that easy to compare. And I will now, in the last few minutes before we take a break, illustrate why this, the fact that you get the identity function here, why that's relevant for calculating in a simple way as well. And that's because we can actually read these types as basically numerical expressions. So if I take this type into the comment, so pairs is basically a product type. So product means that this is if we take, let's put it this way. So we've written functions in both directions, both ways, from a pair to, oh sorry, no, now I copied the wrong one. I wanted this top one here. Okay. So we've written functions in both directions between these two. And a arrow b can also be read as b to the power of a. And pairing can be read as multiplication. So this is c to the power of a. So b to the power of a times c to the power of a equals, well, what do we have here? Here we have b times c to the power of a. So this expression here is about cardinality. So the number, cardinality equals the number of elements in the types sets. So the number of functions from a to b is b to the power of a. If b is the number of values in the type b and a is the number of values. Maybe I should write capital A and B here to avoid confusion. So this is one of the exponentiation laws. If you want to multiply, if we have b times c to the power of a, well, b to the power of a and c to the power of a. So it's equal to b to the power of a times c to the power of a. So there is an interesting hidden correspondence here between certain type expressions for polymorphic types and algebraic identities, which we will not dive deeper into right now, but which I think is fascinating and has lots of implication. Also something called the isomorphism between sets. Okay, we've reached now the end of part 2 here, and I think it's a good time for a break, especially since the schedule said it would be an hour of lecture until 1700 and then another hour from 1730. But I'm open for questions and comments if there is anything more. Okay, welcome back after the break. There was a few questions which were not heard, so I can mention just briefly that one question was about Turing completeness. So Turing completeness is about can the language, and usually for a domain-specific language, it cannot. Completeness. But I've so far not introduced any domain-specific language. So Haskell is a general purpose language and Turing complete. But I will later introduce a few sub-languages which are definitely not Turing complete, and they are domain-specific, very small languages because we don't fit very much in this mini course. There was one more question which I have forgotten now, but maybe it will pop up later. Okay, so third part about in this little introduction to Haskell by polymorphisms and types is sum types. So I was talking about pairs, which is a product type. So basically pairs and records are product types. And one way of explaining that is because the number of elements in the Cartesian product is the product of the number of elements in the subsets. So if you have the pairs of A and B, so there are, so basically cardinality of A times cardinality of B is the cardinality of A comma B. So if you multiply the number of elements in A with the number of elements in B, you get the number of elements in the pairs of A and B. For some types, it's addition instead. So you add values together instead of multiplying them. And the first example is a simple example that comes up often, the maybe type. So it's the idea that it's for situations where you maybe have a value of type A, but you're not sure. So you have to handle this if there is no value case in some way. And the data type declaration here is not finished, but it can be written as either you don't have anything, well, nothing, or you just have an A. And that syntax with the bar here means that there are two possible values, two possible forms of values. So the set of values of maybe A is the set of the value nothing, and then just, so let's say, for example, maybe weekday. Maybe weekday. So it's nothing, it's just Monday, just Tuesday, just Wednesday, and so on, up to just Sunday. So basically, these are the values in the type maybe weekday. So we have the cardinality of weekday equals 7, and the cardinality of maybe weekday equals 1 plus 7 equals 8. So maybe the maybe type constructor takes a type A and adds one extra value called nothing. That's often used when you need some kind of error handling or some default value. You may have a data stream, but sometimes there is no value coming in, and then you have to substitute that with something. And then you can use the nothing constructor, and then later you might fill it in. And there is a standard function that's used for maybe types, which is called maybe with a lowercase m. And it has a bit of a scary type, but this again is designed to have only one correct implementation. So maybe takes a default value, which I call def, and some action function I called action here. And then it takes a value of type maybe A, so mx, and then it should return some value of type B. And now I would use what is called pattern matching again. Before I used pattern matching on pairs. Now I use pattern matching on a sum type. And what happens is basically, instead of writing just one definition here, I write two. I say, well, this is either nothing, in which case I return the default value, or it's just x, in which case I return action applied to x. So this is the sort of only type correct definition we can make. And the reason I've included this action is just to make sure that I cannot make any mistakes. So the A here in the maybe type, I cannot just return it. I have to do something with it, and that's the action. A typical example you might want to protect against is, say, division by 0. So safe div, perhaps. If you get two integers, and then you want to produce an integer, and you want to divide, well, then it's a bit difficult. You might do a maybe int and say, if the first is called x and the second is 0, then you say nothing. And if you have x and any value else other than 0, then you can say just div x, y, or, well. Now this will not be quite type correct here. Oh, parse error. I forgot one of the colons, because integers cannot be divided. So I'll if I want to do this, I should replace int by double instead. So floating point numbers. Okay, and now it works. Now it will check if the second value is 0, in which case it will return nothing, and otherwise just the actual division. Now it's not very practical perhaps for numerics to do this, because you get this maybe constructor in the way. But there are lots of other cases where you have an error value you want to introduce. Okay, so that was the sort of maybe type, and then the last example is the either type. So either is a generalization. It's basically A plus B. So it's a union or disjoint union, also sometimes called a tagged union. So either AB is a type which is either left A or right B. And what does it mean? Well, I should have this kind of example again. So the type either weekday bool. Well, let's put it the other order. Either bool weekday contains the values left false, left true, right Monday, right Tuesday, and so on up to right Sunday. Maybe I should indent it suitably. And you can see that the cardinality, the number of elements in this either bool weekday, is the cardinality of bool plus the cardinality of weekday equals 2 plus 7 equals 9. So the same case setting as we had before, but for addition instead of multiplication. And this is when you want to store different kinds of values, for example, in a list, then you can combine them in this way. I will not go into defining this either function here. It's very similar to the maybe function above, and it has the same kind of pattern of only one choice being possible to make. Because I want to get over to something a little more mathematical and start getting closer to our first real DSL embedded in Haskell. So I will move to another file, complex. So this file is again some live coding. It's from the chapter 1 of the book. It's from week 1 of the course. I've inlined a few quotes from an actual math book, the Calculus book by Adams and Essex, that the computer science students were taking in their maths course, which they took before this course. And I'm trying to, well, you could say, make fun of the math book a bit here. It might be a little bit evil, because I'm really reading the math book as the devil reads the Bible. I'm trying to find anything which seems strange and trying to sort of really read every letter and find out what it means. So the first quote here, and the aim of this is to introduce some Haskell and some coding, and after half of this appendix of complex numbers, we will get to implementing a domain-specific language for complex numbers. But the first quote says, actually the quote is from my book, which in turn quotes Adams and Essex. So the indented part, we begin, that's the quote from the math book. So it says, we begin by defining the symbol I, called the imaginary unit, to have the property I squared equals -1. Thus we could call I the square root of -1 and denote it square root of -1. And it says, of course, I is not a real number. No real number has a negative square. Okay, so I'm trying now to see if we can implement something in Haskell, which step by step will build up towards being able to compute with complex numbers. But so far, from this very little, this 5-line quote here, the only thing we know is that we got something called an imaginary unit. It says it is not a real number, but it does not say that it is a complex number. So mentioned complex numbers, strictly speaking. Strictly speaking. So therefore, I introduce another data type called imag unit. So this is the name of the type, and IU is the name of the constructor of a value of that type. So if we want to write this as said before, so imag unit is basically equal to the set of only one element, and that's IU for imaginary unit. Okay, and then I define a lowercase I, which is equal to IU. And the reason for not writing little lowercase I here is that Haskell does not allow data type constructors to be lowercase letters. So this is a bit of a annoying detail. But anyway, IU is now an imaginary unit and little I is the same as IU. So I can choose to use little I if I want to. So this quote leads me to introduce this new type. And it's often useful when you get to a mathematical concept, or for that matter, something else that you need to implement, a communication standard or a trading rules for some monetary exchange, to take the definitions and try to represent them as types. So let's see. We have this type, and then we go to quote number 2 in the book. Then they say what a complex number is. Okay, this is a little bit strange, but we'll try to deal with it step by step. So it says a complex number is an expression of the form a plus bi or a plus ib, where a and b are real numbers and I is the imaginary unit. Okay, so I was the unit we had before, and now they're saying a complex number can be written in 2 ways. Okay, I've tried to code that up here in Haskell and saying the data type CB, so version B of complex numbers. I actually had a version A before, but I've skipped it now. It has 2 constructors. There are 2 different ways, just like left and right in the either type. So the first form, this was written in Swedish before, second form. The first form has 2 real numbers and an imaginary unit, and then it becomes a complex number. And the other one has a real number, an imaginary unit, and a real number in that order. So the examples here is 3 plus 4i could be represented as plus i1, 3, 4i, and 3 plus i4 is 3i4 with the plus i2 constructor. So there are 2 different constructors, 2 different ways of building complex numbers. I mean, for anyone who actually knows what complex numbers are, this is a bit strange. I mean, why should we care if the 4 and I are in one order or the other? But so far, we just try to use the definition, and for some reason, the definition talks about an expression of one of these 2 forms. Perhaps this means that multiplication, the bi and ib, is actually not commutative. So it might be that bi is not equal to ib. We don't know. So let's be sure here and encode both of them. We should also notice that they have not said that numbers, so let's see here, note that bi plus a is not of the right form, which is a bit strange. I mean, we would expect bi plus a to also be a complex number, but if we strictly want to look at this definition, it only says there has to be a real number, a plus sign, a b and an I, or a real number, a plus sign, an I and another real number. bi plus a is not. Then you would expect addition to be associated or to be commutative, so you can swap the orders, but so far, strictly speaking, that hasn't been introduced. Okay, so we got these 2 constructors and we got 2 example values. Let's try to see if, whoops, now I have accidentally closed my Emacs window, so I should open it again. Complex. Good that I got this cheat sheet down here that checks my font size. Okay, complex numbers back there. And then image mode. Okay, quote back. So what I wanted to do, where I accidentally closed my Emacs buffer, I wanted to check what the evaluator says with C1 and C2. So this prints 3 plus 4i and 3 plus i4. And how does it do the printing? Well, actually, this is another example of a Haskell function defined by pattern matching. So show CB is a function that takes a CB value, which has either this or that form, and then produces a text representation, a text string. It shows the value A, a plus sign shows B, and the I character, and so on. And then it tells Haskell that anytime you want to show a value of this type, use this function show CB. So that's just for convenience. Okay, and then we get some examples. This is the third quote. Now this gets a little bit interesting, especially as we said that bi plus a and so on is not the right form. Here we continue with examples. 3 plus 2i. Okay, that seems fine. We can write that. Here is that example. 3, 2, iu, and the plus 1 form. But then comes something strange. 7/2 minus 2/3 I. Notice that this is not of the form. I have to split this one so that we can see the quote and the second quote at the same time. This has a minus sign in the middle, so it is not an expression of this form. So according to the math book's own definition, this example of a complex number is not a complex number. So clearly that is not what they mean. As they claim that this is a complex number, there must be some rule which makes this reasonable. And you can guess the rule that if there is a minus sign, they mean the same as having an addition and then a negative coefficient. So this 7/2 plus minus 2/3 I is what they mean. But it's a bit tricky that they actually don't include the minus sign in the definition of complex numbers. So I think this is an example of a math author who has not really thought about the difference between syntax and semantics. It sounds like they're introducing a syntax here, syntactic plus sign, the order of B and I, and so on. But in fact, that's not what they mean. Okay, already the second example here did not match, so we have to be a little kind and interpret this as plus a negative real number times I. Then they got this example, I pi. And that's definitely not of this form. There is no I and there is no plus. But then they say explicitly, well, when we write I pi, we mean 0 plus I pi. So then we can notice here that we can represent this third example with the second constructor. Notice why the second constructor? Well, because the I is before the B. Okay, and then the last example, -3, which is also definitely not of this form. There is no I, there is no plus sign. Well, then they define it to mean -3 plus 0i. So these conventions are all fairly normal, but it's interesting to see that they do not really explain these. Rather the opposite. They say that these are the only complex numbers, and then they suddenly introduce numbers which do not follow this form. So unfortunately, this is rather common in math books. You will have to be very careful in reading between the lines. You will have to see, okay, what do we think they really mean instead of what they actually say? Anyway, if we are a bit kind here and interpret these things in the right way, this is the 4 examples they've got. So the last example there was -3 plus 0i. So we have now this E1 and E2 and E3 and E4. And as you can see, implementations in the computer are approximate. So we will only get a finite number of digits approximation of 2/3, for example. And pi also is just a finite number of of digits. Okay, so far so good. We've introduced some examples and this type. Quote number 4. This is a bit of a strange comment. We will normally use a plus bi unless b is a complicated expression, in which case we will write a plus ib instead. Either form is acceptable. Now, if we compare with the quote up here, quote number 1, it's said that a complex number is of either these form. So of course either form is acceptable. It would be silly to first say that both forms are acceptable and then say that either form is acceptable. So they actually mean something else. So what they actually mean here is that either form is equal to the same complex number. It's not only acceptable, they are equal. So what they're suddenly saying here is that, well, we said that there are two forms of complex numbers, but we didn't really mean it. In reality, there are lots of forms. You can use a plus, you can use a minus, you can use no A and no B and so on. And there are certain rules for equality, but there are no different forms. There is just one form in the internal representation of complex numbers, and that has two real numbers, one of them being the real part and one being the imaginary part. And this is a bit tricky because you will have to read that between the lines. They don't say it in the book. So you will have to see, oh, either form is acceptable cannot possibly mean, strictly speaking, that they are acceptable, because that's already clear. It must mean something else. And we interpret it as being these two forms are interchangeable. Whenever you have a plus bi is equal to a plus ib. And what they haven't written, but we can also infer, is that actually a plus ib is also equal to ib plus a. So the order of addition is also possible to change. So we can use this to implement a new type, data CC here. Notice that CB and CC, so I will sort of give up on CB that I had before and now use only CC, because it's easier to program with just one constructor. And then what this, instead of acceptable, if you read it as interchangeable, that means that we can check the equality of two complex numbers, one having real part A, imaginary part B, and one having real part X, imaginary part Y, by checking that A is equal to X, the real parts are the same, and B is equal to Y, the imaginary parts are the same. So this is a Haskell definition which makes us possible to do equality check of, say, plus I 1 0 and plus I 0 1, and it will say false because those are not the same complex numbers. But if we would say 1 and say 1 minus 1, that's true. So that those two complex numbers are the same. 1 minus 1 is 0, so that's 0, and 1 equals 1. Okay, we move on. It's often convenient to represent a complex number by a single letter. W and Z are frequently used for this purpose. Now, this first sentence is a little bit strange here. I mean, of course, it's convenient to represent a complex number by a single letter. We can represent functions by a single letter, real numbers by a single letter. Anything in mathematics can be abbreviated to a single letter. It has nothing to do with complex numbers. So I think it's a little bit misplaced to say that we can represent a complex number by a single letter. It might be helpful to say that W and Z are frequently used, because in the math books, they rarely give types. But here they say that, well, if you see W or Z, you should be suspicious that these are perhaps not real numbers or integers. They are probably complex numbers. Okay, that's the first sentence. That's already information. The second sentence says that if A, B, X, and Y are real numbers, and we have a complex a name of a complex number w, which is a plus bi, and z, which is x plus yi, then we can refer to the complex numbers w and z. Well, we can refer to them or we cannot refer to them, but of course it should work. They have already introduced these forms up here, a plus bi and x plus yi. And then it says also what we already implemented is the equality check. W equals z if and only if a equals x and b equals y. And that was precisely what we wrote here. A equals x and b equals y. So here finally they say that, well, there is only one way of writing the real number, the complex numbers, and they only have two important components, both real numbers. Okay, finally, they've introduced this notation of w and z, and they want to define the first little helper function on real numbers, or on complex numbers. So they say definition. If z equals x plus yi is a complex number, where x and y are real, they have to be explicit here because they could be complex, that would be complicated. We call x the real part of z and denoted by re of z. And we call y the imaginary part and denoted by im of z. And then they say, this is basically using pattern matching. They say the real part of z is the real part of x plus yi, which is just the x. And the imaginary part is the y. And if we want to implement that, this is perhaps a little unfamiliar syntax, but we're saying here the real, so first, okay, we use re and im with the lowercase I, and that's again due to a limitation in Haskell. Normal function definitions can only start with a lowercase letter. So I can't really implement the re with a capital R here. I have to write re with a small r. But they have a type. They take a complex number to a real number. Both re and im do that. And then I can pattern match. I can say the real part of z, and this @ sign means basically this equality here, saying z is actually equal to plus I of x and y. And that whole definition of this function reapplied to z is the x part of the real number. So I bind three variables, z, x, and y, and I ignore the value of z and y, and I return x, and similarly for im. So if I now want to test what is the real part of plus I 1, 0, not very surprisingly, it's 1, and the imaginary part is 0. Okay, and then a first use of pattern matching in more interesting case, the sum and difference of complex numbers. So let's see if we can implement addition of complex numbers. So first, the type here, which they don't write in the math book, but they write it in text. They say if w and z are complex numbers, then they describe how you get a new complex number as their sum. So here we can say, well, you take two complex numbers and you return a new complex number. So two inputs, one output. That's how to read the type. So the two inputs we should write here, so we can call them w and z. But actually, we know that w must be, we can scroll down a bit up here. It must be of this type cc. There it is. It must be the constructor plus I. So we can say w is a plus I of, they used here a and b. And z is actually a plus I of x and y. So now we've copied this text and the left-hand side of the definition. And then we have to produce an answer, something else than error. So this should be plus I of two expressions. And the first we just read off there, a plus x, and the second is b plus y. Okay, let's now try this. We have add cc of plus 1, 0, plus 0, 1. Okay, I forgot it was called plus I in both cases. Okay, so if you plus I 1 0 with 0 1, we get plus I 1 1. Okay, not very surprising. I should remove this one. We have sort of step by step now built up a few example functions and data types that represent what's actually the semantics. So we can say down here, we define semantic complex numbers in Cartesian form. And now we will turn to the first DSL, the syntactic complex numbers. So I mentioned earlier that the DSL has three parts that we will look at: an abstract syntax type, which we will call CE, complex expression. Complex expression, that's what C and E comes from. And then we have the semantic type CEC, which we already introduced. And then we should write an evaluator, eval, that translates an expression to just a complex number, semantics. So I've here already written the data type definition. I will try to explain it. So this is a recursive data type. So the data type CE consists of basically trees. So we can give some example expressions here. I think I got E1. No, those were up there. Okay, so let's write some expressions ourselves. So complex expression 1 is of type CE. So it can be add I. So CE1 here is add I. So that's just a syntax tree. It doesn't really have any meaning so far. And we can define, well, we can take more examples here, CE3, CE4, all being of type CE. So CE2 could be mul II. CE3 could be add CE1 and CE2, and CE4, well, what should we take? You could say add rcon 2 and I. So rcon 2, the intention here is real constant. So the idea is that every real number can be treated as a complex number. So basically this is called embedding real constants. So this converts a real number into a complex number expression. Okay, so all of these examples, CE1, CE2, CE3, CE4, they are just expressions. It says there, add of add II and mul II. It doesn't evaluate to anything. It just is. It's a tree-like structure. It's a bit of like a very small program. It says that, well, I would like to compute the addition of CE1 and CE2, but I haven't done it yet. It's just an expression. Okay, and then we want to evaluate this. We want to write the function that takes a complex expression and returns a complex number. So there are 4 different cases, and we will start with the simplest one, or maybe the second simplest one, I. So how do we construct a value of type CC that should represent this? Well, I will split the screen here. I will search for data CC. So we can see that CC has one constructor plus I. So the answer here must be plus I something something, question mark, question mark. So the real part and the imaginary part as real numbers. So 0 and 1. Okay, so we have now implemented the first case of the evaluator. We can now write eval of I, and that's plus I 0 1. Well, not very fun. I mean, if you try to evaluate anything else, like evaluate our first example, for example. No, not E1, CE1. It will say to do, because this is not implemented yet. Addition is not implemented. But let's try to do it. Let's move to addition. And here is where I would like to use wishful thinking. So it's a design pattern for writing recursive functions. So assume that we've already solved the problem of adding complex numbers. And we call that function addCC, because we've already implemented addCC. I think it's here. So we have a function that would take, so this one needs 2 CC values. So values of type CC. So how do I get a value of type CC? Well, we can call ourselves recursively. We can evaluate E1 and we can evaluate E2. So if we recursively go through this syntax tree and evaluate the first component, and we evaluate the second component, those will be 2 CC values, and they can be added using addCC. So that means that now we should be able to evaluate CE1. So notice CE1 itself is add II, but eval of CE1 has real part 0 and imaginary part 2. So it just added up plus I01 and plus I01 to plus I02. So we can here step by step try to introduce what it should be doing in the different cases. And in this case, for example, the rcon, that's a plus I with the real part R and imaginary part 0. That's what I mean. That's what is generally meant by embedding real numbers as complex numbers. So with that in place, let's see, is any of the 3, 4... yeah, we should be able to evaluate CE4. So this is now plus I2 and 1. So notice that, well, CE4 here has a real, completely real number 2, and then a completely imaginary number I. So this just becomes 2 plus I. I mean, this is real part 2, imaginary part 1. Okay, so the only thing remaining here is multiplication, but we can already implement it structurally. We can say, well, it has to be the multiplication of evaluation of the left and evaluation of the right, or the first and the second arguments. So the form of it is already clear, and the type is actually also clear. So we had addCC before, and now we only need to implement mulCC. And I will now forget these so that we can get the exercise of filling them in ourselves. But what we do know already, well, okay, let's cut even more first, just to see how this is done in similar way as we done in the other Haskell intro file. So we need to take 2 complex numbers as input. Notice here there are complex numbers, not complex number expressions. So they are both of the form plus I, say A, B, and plus I, X, Y. And then we have to write plus I something real and something imaginary. And we can locally define the real part and the imaginary part. And if we manage to find definitions here, then the evaluator will recursively do the right thing. And usually the way this is done, let's make a comment here locally and say, well, if we have, now I will write sort of mathematics in Haskell for a little while. So A plus IB or a plus bi. This is supposed to be the multiplication of a plus bi and x plus yi. And we know by distributivity, that it will be 4 different terms. So it will be ax plus ayi plus byx plus biyyi. Right. Now I just multiplied them without writing multiplication signs, because usually in mathematics it's elided. So the key now, so this is distributivity. I'm just trying to argue now why the definition, what the definition should be. Okay, and then say simplify. So when I said simplify, I want to collect terms in a polynomial in I. So this first term, ax, doesn't have any I, so it's a 0th degree polynomial. And then we have ay plus bx times I. So that's the sort of linear term. And then we have by times I squared. So that's a polynomial in I. And then we know I squared equals -1 plus simplify. So then we can say, well, this is actually ax minus by plus this. So we have now an expression of the form that they were talking about before in the first quote, actually. Let's see if we can fit it in here. I shouldn't have split it so much. This is the ax. Okay, so now it's on the form some real number plus some real number times I. So now I can use this to say the real part is ax minus by. I just have to come back to Haskell and notice that multiplication needs a letter. And similarly here, ay plus bx with multiplication signs. So this is the motivation for why it should say that. Okay, so, and I've just introduced these names, real and imag, but you know from before that I can also splice them in. We don't have to have these separate names if you don't want to. Okay, now it should be possible to evaluate all our examples. So E1, EC1, no, what was it? CE1. Okay, so CE1 is the first, and then we should evaluate CE2. Okay, now this is interesting. So CE2, that's the multiplication of I, so that's basically I squared, which should be equal to -1. And we can see here, it has the real part -1 and the imaginary part 0. So that's an indication that we did the right thing in implementing mul-CC here. Because clearly we could make a mistake. It might be plus here. If we do make that mistake, Haskell will not complain, but it would just do the wrong thing. Now suddenly I squared is equal +1. That's not good. So Haskell will not do magic. It will not discover what you intended to implement unless you make sufficiently polymorphic types. Okay, so that was CE2. We should evaluate CE3. So that's the sum of CE1 and CE2, and that has real part -1, imaginary part 2, and then finally evaluation of CE4. Well, we've seen that before. That's plus 2, 1. Okay, so we've now managed to implement, this was perhaps stupid to have inside the code block. I can make it outside the code block instead. So the exercise here of implementing multi-CC has been done. We've got a complete evaluator which recursively traverses this tree, which could be quite large. I mean, if I do CE5, which is the multiplication of CE2 and CE2, and then CE6, which is the multiplication of CE5 with CE5. So CE6 here is the multiplication of multiplication, blah, blah. Yeah, it's a big multiplication. It's actually I to the power of 8. But evaluating it is no problem, and it becomes +1. Actually, interesting detail of floating point numbers. It actually has the imaginary part -0, which is equal to 0, but it looks a bit fishy. Okay, so if you sum this up, we have implemented a DSL, a very, very simple language, and this is the complex expressions language, which has addition, multiplication, embedding of real constants, and imaginary units. And with that, you cannot express everything in the complex numbers. I mean, I haven't got square roots or sine or cosine or exponentials and so on. But it's showing the basic structure of how to implement a small language. You add syntactic constructors, add Malkorn and so on. And then you write an evaluator, which will, using wishful thinking, which should basically recursively call itself, will implement addition, multiplication, and so on, and translate these syntax trees into basically, in this case, pairs of real numbers, which is the internal representation, the semantic representation of the complex numbers. Okay, now I think this is enough because there's another topic that starts after this, so I think I'll take questions here. Thanks for the invitation, and this is now the third and final lecture of the mini course, and I will talk about domain-specific languages of mathematics today, and I will have a few slides about limits of functions and towards derivatives, and then we'll go to some live coding of another domain-specific language. We did the example of complex numbers yesterday, and we will do the example of simple one-argument functions and symbolic derivatives today. So, as for the previous example, we start with a math book quote, the limit of a function. So this is again from Adams and Essex, and this is not supposed to be something new. It's just something you might remember from long ago or so. And we try to tease this apart and see how we can type it and analyze it and then code up parts of it. So the quote says, we will say that f of x approaches the limit L as x approaches a, and we write, well, this expression if the following condition is satisfied. And then it starts to write something in logic, but with text. So for every number epsilon greater than 0, there exists a number delta greater than 0, possibly depending on epsilon, such that blah, 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 then x belongs to the domain of f and this condition should hold. And if you want to sort of make sense of this, it's good to try to translate it to a more controlled language, not just flowing text. So if we take away most of the words and go towards using logic as the language, then this is what remains. So the syntax for the limit expression, and then it says if, and I use the for all symbol, epsilon greater than 0, there exists delta greater than 0, and then it says such that if, I didn't know exactly how to translate that yet, and then we have this condition, and then in symbols, x should belong to the set which is the domain of f, and And here is this expression which basically says the distance between f of x and L should be at most, well, it should be less than epsilon. And if we want the intuition here, this says that if we wiggle around a bit, we take x close to a, but not exactly a, then f of x should be close to L, but not exactly L. So we have a limit, a certain error in a sort of accuracy in the x direction, and we have another accuracy in the f of x direction. And if we can, for every accuracy, as small as we like it, we can always find a delta, then this limit is defined. Okay, so the first attempt at translating this to some logic expression. So this looks perhaps like Haskell, but it's actually not Haskell because you cannot write for all and exists in Haskell. So it's pseudocode. It's some logic language. It's more of mathematics. But I try to write it so that it looks like a functional programming definition. So we have the limit, and I've changed a little bit from the previous slide. Here it says x arrow a, f of x in L, but the important components here are a, f, and L. So I've taken those a, f, and L as arguments to a predicate. So a predicate in logic, that's something that can be false or true. And it's depending on what a, f, and L are sent in here, it can be false or true. Okay, so then it's defined to be for all epsilon exists delta, and then I've defined a little helper predicate P here. That's a local definition. P of epsilon and delta is, and then what we had before. And we used an implication arrow here for the text such that if then, that seems reasonable to use an implication arrow. If this holds, then this should hold. Okay, so as this is not Haskell, we can't check if it's correct in Haskell, so we have to do it by hand. So the first thing to do is what is called scope checking. So scope is about when variables are defined and bound. So the expression here at the end, all the variables appearing there have to be named somewhere. So first of all, A, F, and L, they are arguments to lim, so they are bound already in the definition of lim. So that takes care of 3 of the variables. And then we got a for all, which is a binding construct. So epsilon from the for all, from inside this point dot, epsilon is a bound variable. It has, you can think of it as having a value. Similarly, exists binds delta, this delta, and then in the local definition, we bind epsilon and delta again. So in here, we bound A, F, L, epsilon, and delta. And then we should check, is there anything left? Is there anything missing? And if we try to see got 0, well, that's well-defined. Less than is well-defined. This is the absolute value. That's well-defined. Subtraction is well-defined. But what is x? So x has not been mentioned anywhere here. A, F, L, epsilon, delta. So x is sort of hanging loose here. So there is something fishy going on. We have to decide. So we can go back and look at the text. It just said such that if this, then that. But it never said how x came into the picture. So this is a very common but rather subtle peculiarity of mathematical text, that sometimes when you say if then, the condition has a hidden quantifier. So a quantifier, that's like for all and exists and so on. And in this case, the hidden quantifier is a for all. So we actually need to add for all x for this to make sense. So now we bind A, F, L, epsilon, delta, and x. Because otherwise, if we don't bind x, it will not be well-defined, the whole predicate. And then I just made up another name, Q, here for the 3-argument predicate, taking epsilon, delta, and x, which now is well-scoped. So x, a, delta, are all defined, and also these F, L, and epsilon are available in the context. Okay, so this is a way of coding up the predicate, and hopefully one might in the computer be able to check for particular AFL if it holds, but it's not necessarily implementable. The lessons learned here is one needs to be careful with scope and binding, in this case of X. And one can also analyze the types here to see that epsilon is a real number greater than 0, delta as well, and X is a real number. But we will not go into details of the typing here because we've done that a bit before. What I would like to look at is the typing of lim. So actually, I have here written 3 different possible types of limit. So I've made them a little bit different. So this is a red underlined lim, this is a blue underlined lim, and this is a black lim. So, and I call them lim prop, lim maybe, and lim sloppy. So in actual mathematics text, the sloppy version is mostly used. So what the sloppy version is doing here is saying if you have an A and an F, then you compute the limit. So the limit is the L that comes out of it. And that's conforms to the notation we saw before. Maybe a little more Haskell-like. You might remember that I used the data type maybe yesterday. Maybe is for things where it might be a value, it might not. So you can have just a value or nothing. And as we know, not all functions have limits at each point. It's more fair to say that actually this function lim returns maybe a y. If it has a limit in this point, it returns that limit. Otherwise, it says nothing. And then the third variant is the one we actually showed on the previous slide, which has 3 arguments. So A, F, and L, and then it becomes a proposition, something which is true or false. So here we cannot compute the limit. We can only check. If we have a hunch, well, the limit might be 2, then we can put in 2 as the third argument, and then we will get true or false out. Here we also have the types of the other components. So X is a subset of the real numbers. Y is a subset. A is some value in X that we want to look at the limit for. L is a potential limit of type Y, and then the function goes from X to Y. So we could write F from real to real if X and Y are the full sets of real numbers. But it's a little more easy to see the different properties or different roles the variables play if we see that this is something that comes as an input to the function, and this is something that is an output of the function. So this must be A, and this must be L, and this must be the limit. Okay, so let's analyze a little further. I will not prove these properties, but it's straightforward from the definition to prove that if we take this proposition version of lim and we have as a condition that L1 and L2 are both limits of the same function f at the same point A. So then we can actually conclude that L1 and L2 are equal. So this is saying that lim as a predicate, it's a motivation for why we can use the blue or the black one, because we can only, if we get 2 different values, well, they are actually not different. They are the same. And functions always have to return the same value for the same inputs. And then the third is sort of connecting the 3. So if L is a limit of f at A, then the blue version would return just L, and the black version, the sloppy version, will return L. So this is the sort of way to connect these 3 variants. And if we look at the black version and apply it to one argument, so it has already got the x, the A here of type x, then it takes a function to a limit. And this function, lim A, the partially applied function, is linear. And what does it mean? Well, normally linear means that if you add things if you add arguments, then you should add the results. And if you scale arguments, you should scale results. And that's the case it means here as well. It's just that adding here is some different thing than adding over on the right. Because the limit, that's just a real number. But the function is not a real number. So adding functions is not the same thing as adding variables, adding real numbers. So then the question arises, what is this O plus? So usually with the ring around the plus, you call it O plus. Well, the first step is when you ask what something is to look at its type. So we know that F has type X to Y and G also has type X to Y because they are the second argument to lim. And the second argument to lim always has type X to Y. So that's the first argument to plus and the second argument to plus. But then the result of adding up these two functions is sent to lim as a second argument to lim. So this result also has to be of type X to Y. So, okay, we know what type it has. So what could it possibly do? Well, there are not many choices actually. So if we want to add the function f to the function g, it should be a function. That's what this type indicates. And it takes an x of type x. And then, well, the reasonable thing to do is to run f, to run g, and add up the results. So f of x is a real number, g of x is another real number, and the sum is a real number. And those are all of type y. So this local lambda expression is the definition of the O plus for f and g. So in that way, we can add functions on the left-hand side and add normal things on the right-hand side. Okay, and why is it relevant that it's linear? Well, I won't go into details here, but in the course we go further and conclude from this later that the computing the derivative is also a linear operator. And we will look at the other half of defining the derivative now. So this is now the second quote for today's lecture. It's a math quote from the same book, and it says the derivative of a function f is another function, f prime. So notice here, it doesn't say f of x or f prime of x. It really says f because that's the function, and f prime is another function. And then it says, okay, how is f prime defined? Well, if you give it an x, the value should be defined by this limit. And here we're back to the classical mathematical notation for the limit, which we will try to avoid because we want to be checking the types corresponding to what we've done in the previous slides. But we will start from this and then try to make it look a little more like Haskell. So the first step is that the task of this definition is to compute the derivative. And as they say, the derivative of f is another function. The derivative computation is also a function, a higher order function. And right now, the only notation in the definition here is a prime, and that's a little bit hard to read. So I will instead call it capital D. So D of f is the same as f prime. So this left-hand side here, dfx, is the same as f prime of x, the left-hand side there. Okay, and now I'm trying to use the black, the sloppy version of the lim, which has a point where we take the limit and the function. And then we have to see, okay, what is the point? Well, actually, the limit is when age approaches 0. So a here is 0. And what is the function? Well, it's not f. So the function we take the limit of is this expression. So we can define the function g here, saying, well, if you give me an age, I will compute this quotient. So notice here, the type of age is basically all real numbers except 0. Because if we would get age to 0, this will be undefined. So we can compute the limit when age goes to 0, but it's not defined for exactly 0. Okay, so the quotient is the usual one for derivatives. We take the value a little bit away from x at x plus age and subtract the value at x. So that's the difference in the y direction if you have an xy graph. And age is the difference in the x direction. So x plus age minus x is age. So the difference divided by the difference means that this is the slope of the function. The slope of segment between 2 points in the function. And when age becomes smaller and smaller, this will approximate the tangent, which is the derivative. Okay, so g has type, well, g is a function. It has type age to y, where age is all real numbers except 0. Okay, so that's the first step. Let's then try to step by step look at this definition and see if we can make some reusable component, because this g here, it's a local definition and it doesn't have x as an argument, which may be a little strange because x is used in the definition. So let's add x as an argument. And if you look at the first line here, where it before said g, it now says phi of x. So I just defined phi such that phi of x is the previous g. So now we have x as an argument, but the fact that it's phi of x in the limit computation means that x will not change when we take the limit. Only age will change. Okay, and if you look at the types to make this work out, it means that phi takes an x and returns a function from age to y, a function we can use in the limit computation. And actually, we can make use of the composition, the function composition operator. This was a dot in Haskell. It's a mathematics, it's usually written as a ring. So this is a function, lim0, phi is a function, and we have an x argument here and an x argument there, and we can get rid of those and just say, well, the derivative function is phi composed lim0. So this is just a simplification to make sure that we can define in the same vein as we had before the function f prime, the function derivative of f. And this is that function. Okay, we're almost done in extracting a reusable top-level function here, but there is still one argument that phi doesn't see. So we have a local definition of phi, and it uses the f up here, and it's not visible as an argument. So let's change it again. So now we'll invent yet another function name. I call it psi. So phi is equal to psi applied to f. So now we'll have to be careful. We have a 3-argument function psi. Psi of f, x, and age is this quotient. It's the same quotient all the time, but now psi has all of the arguments in place. So now it doesn't have to be a local definition. It's a top-level thing we can analyze separately, and it has nice properties of linearity, for example. So the linearity of derivative, which we'll not go through here, comes from the fact that limit is linear and psi is linear. Anyway, this is a way of illustrating the types here. So when we have a function composition, so we sort of apply one function and then another function. Then if we start at the value x, we apply the first function, and we get a function, h to y, we apply limit at 0, and then we get the limit y. And that the derivative is defined as the composition of these two functions. So d of f is here the annotation, the label on the arrow between x and y, and that means that derivative of f has type x arrow y. Okay, so the capital D here is something we cannot implement in Haskell, but if we want to, we can specify it and we can check some properties. For example, if we have squaring, doubling, and the constant 2 function, then the derivative of squaring, which is the capital D about the square, is actually 2 times, which is double. So that's from well, is assumed to be known from other places. And if we take a second derivative of squaring, that's the derivative of square's derivative, the derivative of double, which is the constant 2 function. So these are properties that hold for this function. And the thing is that we cannot implement D of this type in Haskell, or in any programming language, by the way, because it will need to have something more than just a function. It will need to know how the function is defined. So we can approximate it, and I will look at this a little bit in the live coding very soon. But we cannot compute the actual derivative unless we have the source code of f. And how do we get the source code of f? Well, instead of analyzing the full Haskell source code, we will implement our own little DSL embedded in Haskell, so our own domain-specific language for simple functions. And then we can implement symbolic derivative. And that's what we will go to in the live coding now. So let's clear here. I'm now in another file than yesterday. And what I want to do here is motivate the need with working with syntax. I've sort of already done half of it, but I will do it a little more from another point of view here. Remind you about the DSL definition and define a DSL for functions. And using this, we should be able to define a syntactic derivative function, deriv. So this takes a symbolic function to a symbolic function, and it's similar to the D, which takes a semantic function to a semantic function, where the type semantic function is real to real. So this cannot be implemented, but this can and will be implemented. Okay, so the first thing is that, well, if we only have an f in our hand, for this, the motivation why it can't be done, we can't know if this is a sum or a product or whatever it is. And we only have derivative rules for those different cases. So we cannot, we might naively attempt to do pattern matching on semantic functions, but this does not work. And then we might say, okay, let's use this lim and psi from the slides. So we will look at this a little bit, and I will now introduce the 3 functions I had in the last slide: squaring, doubling, which I call tv for twice here, and constant 2. So let's see. If I square 3, it's 9. If I do twice 3, it's 6. And if I do constant 2 of 3, it's 2, not very surprisingly. Okay, and then I define this psi function. So remember, it took a function from x to y, a point x, an age, a small epsilon sort of, and it computes the slope locally. Oops. And this is a very concrete function. I can try to apply it to some example function like squaring. It will lead us astray, but it's a good example to try. So this t1 is a function, so we can apply it to 3, but then we don't get much of a visible result because it also wants an age. So if you apply to 3 and 0.1, then we get the slope near 3, which is apparently 6.1. If we have a larger step, it's 7. If you have an even smaller step, it gets closer to 6. So it looks promising here that perhaps we can actually compute in Haskell the limit by sort of letting the age become 10 times smaller repeatedly until it stabilizes. Unfortunately, due to rounding error, this doesn't quite work. And I'd written a little example code here which does exactly this. So it starts with age being 1, and then 1/10, 1/100, 1,000, and so on. So 10 times smaller all the time. And we can see that it gets closer and closer to 6. Here it's really close to 6. And here, suddenly it goes the wrong way. And then it stays the same, and then it becomes worse and worse and worse, and suddenly it's 0, exactly 0, and it stays exactly 0. So if we would use the idea that, okay, compute the difference here and make the age smaller and smaller and smaller until it stabilizes, well, then it will stabilize at 0. And then we say, oh, we found the derivative. The derivative of a squaring function is 0. But that's not true. The squaring function at 3 has a derivative which is 2 times 3, which is 6. And we get closer and closer to 6 for a while, but then it sort of goes wrong. And we know why it goes wrong, and that's because in the computer we have only an approximate representation. So we have what is called floating point values. So we can't compute exact quotients. And the smaller numbers we get and then subtract these, then the error will be more and more important. And finally, it will be, the error is so big that the result is completely gone. That's the zeros we get at the end. So this illustrates that it's not really possible to compute the derivative exactly using, well, not just using Haskell, but using any of the languages. We have to do something different from this numerics. I should say that if we seriously have to compute the derivative and we don't have the syntax, we could try to say, okay, we know the precision of the floating point, and we can stop, say, after a few steps here with a sufficiently small epsilon and tolerate an error. So that's an option, but we will want to do better than that. Okay, but anyway, we can express the limit computation. The problem is that the limit at 0 cannot become implemented. And that's the reason for that is what I said here, that the smaller we get the age, the bigger problem we'll get with numerical rounding errors due to approximation, well, rounding error. Okay, so then we've motivated, and we're sort of back up here. It says attempt 3, build a domain-specific language. And that's what we will spend the rest of this lecture on. And I promised I should remind you what the DSL is. So I've skipped the 0th part, which was a syntax for sort of the textual syntax, which characters should be written. And I jumped directly to a type of syntax tree. And then we need a type of semantic values. And then we need a function, which is an evaluator from the syntax to the semantics. And then we can do things on the syntactic layer and then translate to the semantics at any point. In this case, we want to compute derivatives. And we saw in the slides that derivatives are computed for functions. So we need actually a domain-specific language for functions. And more specifically here, we want one argument function expressions. So we had yesterday complex number expressions, and now we have one argument function expressions. And the reason I stress this one argument is because we only talk about here derivative in one variable. We can do partial derivatives for n argument functions, but that would be too much to cover in this lecture. Okay, so I will start filling in things here. And just to be concrete, we could start saying, what's an example of a syntactic function? Well, we could have the function squaring. So if we say that all the functions we're interested in the squaring function, then, well, we've just said, okay, all functions are, there's just one function that's called squaring. And it will not be, I mean, we will extend it later, but we can see if we want to implement this, what should we do to write the evaluator? What's the meaning of squaring? So the evaluator has to have one case for each case here. We will add more cases later. So the squaring function semantically is the squaring function. So here I have a capital S, which is just a constructor name. And here I have the lowercase s, which is the square function that I defined before. And you notice here I got semf equal to real. So the evaluator translates from the syntax to the semantics, and it looks like it does nothing. So let's see now if we can use it. So the evaluator of squaring is, well, okay, it's a semantic function. What can I do with the semantic function? Well, I can apply it, for example, to 3. If I apply it to 3, I get 9. So here we can see that eval of SQ is a function that I can apply things to, but eval can analyze its structure to do this. Okay, now I could simultaneously try to give some example of derivative. So I have down here, which is actually barely visible, so let's scroll up a bit. I've said that I also want to compute a derivative, and now I will compute a syntax tree for the derivative. So then we say, okay, what's the derivative of squaring? Well, now suddenly we should have twice the function twice here, because otherwise we can't implement derivative of squaring. So the derivative of squaring should be the function twice. And now we can say, okay, evaluate the derivative of squaring. And it says, it's a function, apply it to 3, and it says, non-exhaustive patterns. So what's happened here is that we've written the evaluator for squaring, and then we added another constructor twice, but we haven't implemented it. So let's add another case. Okay, now we can evaluate the derivative of the squaring function at 3, or for that matter at 17, or at -3, and so on. So, of course, this is not a very useful data type for simple functions. I mean, it only has basically 2 functions, squaring and twice. So we can extend it with the next natural step, C2, which is the constant 2 function, but it is a little bit silly. Why just constant 2? We can be more general than that. We can say constant real, or just to, yeah, let's have constant real. So what would be constant R? What would the evaluation of constant R be? I should just now check also. Well, okay, I have to say error to do. Well, I mean, it has to be a function, so it has to take x in, but it should always return R. So it's the constant function that always returns R. And now if we want to compute, say, the derivative of twice, okay, the derivative of twice doesn't work because we've extended the data type with twice and constants, but we haven't extended the derivative computation. So let's do that. Derivative of twice equals constant 2. And let's check. Derivative of twice is constant 2. And evaluating derivative of twice is a function applied to 3 is 2, applied to 17 or 18 is 2. It's always 2. Okay, so we're getting a little more general here, but having twice and squaring as cases is a little bit silly. A more general case we should have is addition, multiplication, and the variable x. Remember, we had one variable, one argument function expression. So let's add x as the variable. So then it's a question, how do we evaluate x? So the idea of x here should be to return the input. So it's actually take an x in and return x. So it's the identity function. And that's 3. Evaluate x at 17 is 17 and so on. So what can we do for the derivative of x? Well, the derivative of x is the function which is slope 1 everywhere. So it's constantly 1, the derivative. Okay, so this I will actually put at the start of the derivative computation, because this is basically the base case, the most important case. I will move it up there as well and start with x here as well. So in fact, constants, x and constants are more important than squaring and twice. So I'll move up constants as well. And we can see here we have defined derivative for x, squaring, and twice, but we haven't defined derivative for constant functions. So constant function returning r, well, it's a flat function. It's always r. So its derivative is always 0. So its derivative is also a constant function returning 0. Okay, so now we can compute the derivative of squaring. We can compute the derivative of squaring. And we can even compute the third derivative of squaring, which is then constantly 0 everywhere. The first derivative is twice, the second derivative is constant 2, and the third derivative is 0. Okay, well, we only have what is called base cases here. We have sort of a list of possible functions, but it will be a very, very long list if you want to extend it with everything we might want. So the only general case is this constant, that because it has a real parameter. So what we would like to do, or we would like to be able to do, is to add functions. So we have two functions, we should be able to add them together. And the first question then is, so let's move these down a bit, because I think squaring and twice are a little bit special cases that we can remove later. So evaluation of an addition of an f expression and a g expression. Now is the question, what will be the semantics of this? Well, it's always a good idea to use this idea of wishful thinking. Wishful thinking being recursion, being saying, okay, let's assume we have already evaluated fe and ge. So we have eval of fe and we have eval of ge. So those are two functions. And then we want to add these functions together. And I will now say, okay, let's assume we have a function dot plus, which does this addition. So the first we can do is to check if Haskell likes it in the sense of type checking. So the type works. It means that if we can implement this dot plus thingy, then we will have solved the addition case. And I placed the dot plus here. So notice that add up here, I can put that in a comment. Add has type synf to synf to synf. And if I line this up, you can see that the difference is just that we replaced everywhere the syntax with semantics, syntax with semantics, syntax with semantics, but it has the same shape. So this function, f plus g, is actually what we called O plus, in the slides. So it's supposed to add two functions together, and it can do this by taking an argument, applying f to x, and adding it to applying g to x. So this works out type-wise, and now we can try to give some example. And I would actually say E1 here is add xx. Okay, so if you evaluate E1, we get a function. We can evaluate that at 3. Okay, so what function is this? So at 3, it has value 6. At 17, it's value 34. At 1, it has value 2. Well, actually, this is the same as twice. So we add x together, then we get twice. So that means I think actually we can now remove twice. We've covered it in another way. So I will cut away twice from these different definitions and from the derivative definition. But we should now, if we manage to evaluate the addition, we should also be able to compute a derivative of the addition. So add the function expression fe and ge. And here as well, if we can compute a derivative of fe and we can compute the derivative of ge, we should then combine them together to a function. But notice that these expressions are syntactic, so we can't use dot plus here. I can try, and then it will say, well, okay, I should remove that case as well. It would just say that you can't match synf with semf. So I need to add syntactic things together, and that is what the constructor add is doing. So now it works, and now I can compute the derivative of E1. So notice that I can evaluate it here. E1 is add xx, and derivative of E1 is add constant 1, which I guess should be simplified to constant 2. But to be very clear here, we haven't implemented the simplifier. We're just doing exactly the thing which is required so far. Okay, and I mentioned that we would like to have not only addition, but also multiplication. So we can add another constructor, and we can copy this case and write instead mul, and then we need a dot star operator, something very similar to dot plus, and we say a function, so f times g is a function that takes x to f of x times g of x. So if I want to see the similarity here, I can put them next to each other and indent similarly. Okay. So dot plus and dot star have exactly the same type, but in one case it's addition and the other case it's multiplication. Okay, and now we can write another example. We can say E2 is mul xx, which should be the same as squaring. Whoops. Okay, let's load this, look at E2, and then say evaluate E2, which is a function at 3, it's 9. It's x times x, where x means, in this case, 3. And I mean, 17 is 289 and so on. Okay, and now we also need to implement the derivative for multiplication. And actually, well, I should say, as this is the same, I should say this is the same as squaring, then I will also remove the squaring constructor, because it's a bit silly to have a squaring constructor when we already know how to express it more generally. So then we need the derivative of the multiplication of fe and ge. And then first, let's write it roughly here. So if we had a function, if we wanted to compute the derivative of f dot times g, so dot times because that's the operator here for multiplying functions. So we know from calculus that this should be the derivative of f times g plus f times derivative of g. And now if I should be specific, I should have dots times and dot plus and dot times there. So this is derivative of the first and then not derivative of the second, but the first and then derivative of the second. That's the usual derivative rule. And now we have to sort of translate this to what we should do on the syntactic side. So D, if this, we keep this line, and then we said D should be deriv. So everywhere it says D, it should say instead deriv. So D there is also deriv. And let's indent a little bit to see if we can keep the symmetry here. So the addition here is actually the constructor add. So instead of dot plus, we use add. And the multiplication must use mul. So it's perhaps not that easy now to see the correspondence, but if I indent it, it might be possible to see roughly how they sort of match up. So derivative, yeah, okay. Well, actually, I should do mul here as well. Mul fg. So derivative of mul fg should be this expression. So let's copy that one up. And now the only thing different is I call the FE here. So let's write FE, GE, FE, and GE. And that was just to keep track of which one had which type. So F expression is not the same as F as the function. Okay, interesting. Now, can we compute the derivative of the example E2? So let's look. So first, E2 is mul xx, and then this rule will say it's an addition of a multiplication of the derivative of x, which is 1 with x, and then multiplication of x with the constant 1. So yes, it is correct. It might not be very pretty, because I mean, if I take this expression down here, this is actually equal to the addition of multiplication of constant 1 and x and multiplication of constant 1 and x. So the same multiplication twice, which should be the same as the multiplication of constant 2 and x. But I currently don't have a simplifier to implement this. It's an interesting exercise, and it can definitely be done to make a simplifier. So something like simplify, which takes a syntax tree, to a syntax tree. And I would just say here, error, homework. Difficult at this stage, but it's definitely doable. You can simplify these different patterns and make them then go away. Okay, but let's see what we have so far. So we have implemented up here a data type which has x, constants, addition, and multiplication. So we can write rather complicated expressions. Perhaps I should give E3 and E4 as other examples as well. So let's say now we add the multiplication of E1 and E2 with, well, x or whatever, and then we say we multiply E3 by E3. Right. So E4 here is now a rather big expression. It's not a very useful expression perhaps, but it's something. We can evaluate it at 3, say, or 2, or 1, or 0, so on. I mean, it's a polynomial actually, and we can also compute the derivative of E4. It's not a very readable expression. This is where you really would like the simplifier to kick in, but it is sort of, it takes almost no time. You can add the simplifier later, and it shows what kind of things you can do when you got a domain-specific language as a syntax, an evaluator, and the semantics. And then suddenly you can start doing symbolic computations, such as computing derivatives. Okay, so to sum up, the mini course conclusions is that we have talked about domain-specific languages, DSLs of math. We did a short introduction to functional programming in Haskell, very short introduction, just an hour. We've been formalizing or implementing some textbook domains, and with domain examples, first example was complex numbers, where we'd implemented the syntax, the semantics, and the val function for complex numbers. And then these simple functions we talked about today, also syntax, semantics, eval, but also the symbolic derivative. They are called deriv. And this and much more is available online. There is a playlist with lectures from the full course instance from 2022. There is source code repository with all these examples, all the 17 exams of the course, including solutions, if you want to study on your own or ask questions, and the full PDF of the course book, which of course can also be bought on paper, but if you just want to look at it online, then the source code is there and the links are available. And yeah, this was the contents of lecture 3, which concludes the course, and we can take questions.